Okay, so hello everyone. We're Team Galactic Enterprise, and today we'll be talking about what our project was and the steps we took to get there. So before we get into our project, I'd like to introduce our team. I'm Sierra Yao. I'm an 11th grader at John Muir High School, and before this program, I had no experience in programming.
My name is Annie Finelli. I'm a 12th grader at Marshall Fundamental, and I've had one summer course of Python previous to this.
Hello, my name is Will Tamrowski, and I'm going to be a 9th grader at Pasadena High School, and I had some experience with programming before this.
Hi, my name is Tiffany Shi. I'm going to be a senior at San Marino High School next year, and I took an intro course in Python last year.
Hi, I'm Andrea Kova, and I'm the college counselor at New Village Girls Academy. I'm one of the teachers here, and I had no experience in coding before this.
So our project is broken up into about 5 parts, and within our presentation we'll go a little bit into machine learning, and we'll talk about our research, and we'll also talk about the submission process.
What's that?
It's not. Just go to the screen.
Technical difficulties here. I'm just going to go ahead. Yeah. All right, we'll do that. Okay.
Okay. So what our project was we had to classify galaxies using Galaxy Zoo. Then we had to make an algorithm and submit it to Kaggle following their submission lines. And their submission lines there was 11 questions, and within the questions there was 2 to 7 responses, and we had to submit probability. So before we could actually tell the computer how to classify galaxies, we ourselves had to figure out how to reclassify them. So some of the ones we had to classify were spiral galaxies. So notice how there's the arms spiral around this center point. And with an elliptical galaxy, it's kind of shaped like a football, and it's just one color. And when you look at a spiral galaxy, there's like purple and bluish tints. And another way to classify galaxies is their position. So with face-on galaxies, the whole thing faces us, so we can see the arms and the center bulge. And when we look at edge-on galaxies, they're kind of at a pivot. Some other ways to classify spiral galaxies is the movement of their arms. So they could either go clockwise or anti-clockwise. And another way to classify galaxies is if they're merging. So merging galaxies is basically when 2 galaxies crash together. And when this happens, you get these kind of like tails and arms that go out. And you also get these kind of clouds that form around it. And that's one way we classified them. So now we're going to go into background, preparation, and research, and that's going to be talked about by Annie and Will.
So I'm Annie again. So I'll be talking about some code that we wrote for outlining an image, and then I'll be talking about Galaxy Zoo. So this first slide is for our code that we wrote to show us the edges of a galaxy within a picture if it's hard to see that specific galaxy. So this will be the original picture, and then the code will give us this for a black and white pixeled image, so it's easier to see the shape of this galaxy. Next is Galaxy Zoo. It's a citizen-based science project where people can volunteer and give their own classifications of the galaxies. So this project uses different telescopes. So they'll use images from the Hubble Space Telescope. They'll also use images from different databases like the Galaxy and Mass Assembly Survey and the Sloan Digital Sky Survey. And then this is a picture of the Hubble Space Telescope. So next, Will will explain his part.
Hello, I am Will, and one of the problems we encountered during the project is that a lot of the images were really hard to look at. They were blurry, just hard to classify. So we wrote a program that sharpens the images. Now, it doesn't increase the resolution because that's not trivial, but instead it more of like changes the colors to brighten it a little bit, which helps us a lot in for humans to classify the galaxies. And I will be talking about machine learning. Machine learning is also known as AI, or artificial intelligence. Now, during this project, we used a lot of modules that incorporated machine learning, like NumPy, SciPy, or sklearn. These modules, they helped with the algorithms that created the probability with our project. And I will be introducing Tiffany.
Hi, so I'll be talking a little bit about our project approach and what steps we had to take in order to solve this problem. So first, as Will mentioned earlier, we did try to use machine learning in our algorithm. But aside from the obvious challenge that we had little familiarity working with these modules and machine learning, there were a few problems with the data set itself. So first, I'm going to be talking about the first challenge, data volume. So there were 79,975 test images, as well as 61,578 training images. So if any of you have done image processing before, you know that this takes a long time. And when we finished our algorithm this previous Wednesday night, we realized that we wouldn't have enough time to run the entire training and test data. Before the deadline hit. So our first solution to this was to try parallel processing, which is where all of our team members took the same code and we ran it with different batches of images so we could put it all together. And next, since Christine overheard us talking about this, she actually proposed that she could run it on her supercomputer for us. And so that's running right now, and hopefully we'll be getting a result soon. Next, I'll be talking about the challenge of data complexity. So if you recall the image that Sierra showed us earlier, we can see that there are, first of all, 11 questions, each with 2 to 7 responses with them. And because they're all based on each other, they all depend on each other, we have to weigh the probabilities in a specific way that makes the probabilities of each class not equal to 1, but a specific percentage. So this was a challenge in figuring out, and it was specific to each question that we did. So it was one of the challenges that we had encountered, but we were able to apply specific coding to each question and figure it out. Next, the challenge of data quality. So Will touched on this a little bit earlier, but if we look behind me at the screen, we can see that there are 2 drastically different resolution images, and these are both images that were pulled from the test data. So our first solution to this, to clarify it for ourselves, was to do image sharpening, as Will talked about earlier. Our second solution was to develop an algorithm that looked at color values, or RGB values, which would help us, since RGB values aren't really distorted by pixel like blurring or anything, it would help us classify these images in a specific way that we would still be able, the computer would still be able to identify. So now onto our algorithm. So before I get into our specific approach, just a little more background on machine learning. There are 2 main types of machine learning, supervised and unsupervised. In supervised learning, we take training data and associated solutions to predict the output for test data. Whereas in unsupervised learning, we take data and patterns and we try to, it learns by discovering groups and clusters within this data. And so since we were given training data of 61,578 images of training data, we decided to take the supervised approach. And so the way we did this was through the module scikit-learn, which Will mentioned earlier. And so this is a quick diagram of supervised versus unsupervised, where we see that the unsupervised learning takes data and clusters it into groups based on arbitrary or specified patterns, whereas supervised takes a boundary based on training data. So next, into the specific approach that we took. So in scikit-learn, in supervised learning, there's this thing called k-nearest neighbors classification. And this is what we use in order to classify our data. So we fed it the training images, and we let it fit to the specific classification for each question, and then we fed it test data so it would produce the probabilities of each class and its response. And so here's a diagram of, say, if we had a question with 3 responses, we would want 3 different groups, right? And so this k-nearest neighbors classification takes this data and divides it based on the training into the, divides boundaries into these 3 specific groups. And so one of the challenges we had with this was that the training solution data came in the form of probabilities. And so this is just a really quick screenshot of a few images that we got and their probabilities for each class. And this is also the submission format that we had to have it in. And so the way we approach, so the problem with k-nearest neighbors classification with scikit-learn is that it takes discrete values only, which means it only takes integers or specific classes as training solution input data. And so the way that we solved this was that we took each class and its responses and the probabilities for its responses, found the max for them, and we put the one with the max class with the max the probability with the max value with to a value of 1, with the other ones as a value of 0. And so this is kind of how we solved this, though it did lead to some inaccuracy, but it was the best that we could do with the module that we were using. So next, as I said, we're running it on the supercomputer now, so we're hoping for a result that maybe can be posted either this week or next week. But we did have a few ideas for improvement. So we did have a 2-week timeline, which was a little short for us. So we did want to try a few other things in the future. So we were also thinking about different RGB combinations, which would maybe highlight the orange color of elliptical galaxies more, or using the edge contouring that Annie talked about earlier, and using the white pixels and counting those in order to predict future values. And now Annie's going to talk about submission. Thank you.
Okay, so I'll talk about the submission process and the requirements that we had to fulfill. So we had to use the Galaxy Zoo decision tree, which had 11 questions and 2 to 7 responses for each, as my group has said previously. So the first question had all the 3 probabilities that it had all had to equal 1. And based on that path that the picture went through, the sub-questions had weighted probabilities, as Tiffany said before. One of the other requirements that we had was that the format of the file had to be CSV, or else it was unable to be submitted through Kaggle and scored. For Kaggle, we had a max of 5 submissions per day, so if we exceeded that limit, we had to stop and wait till it resetted. And for the final submission, we have to pick 2 specific submissions that we thought was the best to get our final score. So this was our first submission that we took. We put all of the questions in the file, but we only used 5 of the image IDs. And when we put it through Kaggle, we got an error. So this was the error, and it told us that we had to have all 79,975 images within that file. So once we were able to input all of that, we were able to actually get a score. So this was the code that we used. We didn't have probability at this time, so we just had all zeros inputted into that file. But we were able to successfully get a result, and as Tiffany said, we're running the final product with the probabilities on the supercomputer. So now Ms. Andreakova will introduce the summary and the conclusion.
Okay, thank you, team. So as my team has said, I'm going to go ahead and conclude us with identifying some of the resources that we used. But as you can also tell, there's still a lot to go in terms of classifying galaxies. Edwin Hubble created his classification scheme in 1929, which is what we used for this project. And then now it's transitioned to what you see today, which are collaborative online projects through Kaggle. So if you all are interested in pursuing and discovering something on your own, this website we've talked about over and over today is called Galaxy Zoo. You can actually identify a collaborative project and get paid for it, which is really awesome. Had we identified this project about 3 years ago, each one of us may have gotten $16,000. So I encourage you all to go to this website and find some projects on your own. And from this project, as I mentioned earlier, this is the specific one we did. Although it ended 3 years ago, as you can tell up here, it was worth $16,000. We are still able to submit and contribute to whatever code we could. So that's also really rewarding. And as my team mentioned before, we use something called parallel programming. We all work together on this code, and we're able to submit as a unified team. So that's also a really great opportunity. I mentioned before that I had absolutely no background in coding. And so when I was offered this opportunity by Dr. Corbett, it was such a true honor. So I will say that her textbook, which her and her team created, has been a huge support. It is identified up here. We also wanted to thank Sebastian for being our mentor through this process. And Ibuke, you were in that room with us for a long time trying to get through it. So if you all want access to it, I know as Dr. Corbett said, it was a super resource for us. And then if you're like me on the very beginning stages of coding, Python Anywhere is the main source for our code. And these 3 programs are what sometimes we use in our school at New Village Girls Academy. Everfi, if you don't have it at your high school, definitely talk to your coding and math teachers to see if they can implement it for free. Of course, we all know, or we may know about Khan Academy and Coursera, where you, if you're curious today to take your own courses, definitely look them up. And last but not least, GitHub is a really fantastic resource. As Dr. Corbett called it, it is your online coding resume. So if you're interested in getting an internship at some point, or maybe employment in coding, make sure you put all of the things that you work on GitHub, and make sure not only that, it's as detailed as possible, because resumes and employers are looking at this. And if you are 16 years old, even younger, you can still contribute to GitHub. So definitely take a look at that. And then last but not least, questions. So if you are a coder and you feel like you have very specific questions about something you're working on, Stack Overflow is a prime hub for that. You get very detailed responses through discussion boards and other means. And then you also now have a team of hopeful experts in galactic science. So if you have any questions for any of us, you're welcome to ask those now. We have about 2 minutes, I think, of question and answers. So team, if you want to come up here in case anybody has any questions for us, and then you can also catch us in the reception. Does anybody have any questions? Go ahead.
I actually have 2 questions. One, I know that many space images actually come with false color. So I was wondering, did any of the images that you were given have that? If so, how did you deal with the various spectra that you get from those images? And then the second question is, did you guys have an app interface? I saw some of your code there, but I didn't see any screenshots of an app. And I wasn't sure if an app was developed, or were you simply submitting code?
I'll bring the microphone back for you guys, sorry. This is more for the recording. I know that you projected very well, but it's being recorded, so.
So just with our 2-week timeline, we really didn't have a lot of time to look through all these images and see if they had false coloring. So what we did was we just kind of relied the best we could on our machine learning algorithm. If we had more time, this is something that we have thought of, and and we wanted to experiment with in the future. But just for the timeline, since we finished just barely this week, we didn't really have time to experiment with that. And as for your second question, we didn't really develop an app. We just, as Annie said, we had a specific submission format, and you had to submit a specific CSV file or a text file, basically, that had all the Galaxy IDs and their probabilities for each class. So it wasn't really an app. nor did we submit code. It was just the end result. Does anyone else have questions? Yeah.
Dr. Lichtel back here. It's one of our innovation speakers, back for more.
It's trying to be incognito. Hi, no, I'm just kidding. Hi, everybody. That was a really great presentation. Thank you. A question I have is, did you do anything to the images before feeding them to the k-means algorithm? Or k-nearest neighbors, I should say.
So I'll let our image experts talk about the imaging.
Well, for the imaging, we did sharpen them to be used in the final product. And I'll let Tiffany explain this one. But well, we did sharpen the images. We did sharpen them, though.
No, he pretty much answered it. We did sharpen the images, though. When we ran it ourselves, since we kept encountering memory errors, we didn't always include it. Though we did, in our final code that we were trying to submit, we did want to include that. It's just with so many memory errors, every bit of code was kind of resaving an image was just a lot of too much memory for us. We couldn't run more than 300 images at a time, and with another 70,000 to go. So yeah.
And one thing I would also add is Sierra and I started working. Sierra did a good job about identifying the RGBs and the codes for each of the colors, and we noticed that there were very specific colors to galaxies, and so we were able to at least hone in there. But when it came to the code for color, we decided to take the alternate route and just go for all of the classification.
All right, I will invite the next team up to set up their laptop, and let's thank Galactic Enterprise.